We have with us four people with different country, and we have two topics. One topic, efficiency in the pump field, and the other topic, efficiency in the water treatment field. Um, Therefore, we have two parts. Let me present our team today. We start with Mr. Samuel Torelli from Saer Company. Saer is manufacturing pump in Italy. Mr. Torelli has more than 15 years experience in the pump fields, centrifugal pump, and in the industry sector and water management sector. The second expert is Mr. Muhammad Abu Shanab. Muhammad is from Wilo SA company. Wilo is placing in Germany, Dortmund. Is also manufacturing pumps in water and wastewater field. Is very, let's say, has very historical time in the pump field and in water treatment also. Mr. Abu Shanab especially is here, placed in Jordan, is the director from the rep office from Wilo, and he's take care about Jordan and Palestine. So this is the pump field. The water field, we have Dr. Hammam Sulaiman. Hammam Sulaiman is a doctor in power electronic field from Aalborg University, and he's now working by Aalborg CSP and responsible for sales and research. And the last one is Dr. Iyad Zuraiqat. It's not Zaiqat, it's Zuraiqat. Is from TTU, Technische University Berlin. He is working in the share for urban and water management. So we will start now with two topics. The first topic, I just learned that the pump, centrifugal pump, has a share of worldwide 20 until 40% from the total electrical consumption. Yeah, you can agree with me that this is of course different from country to country, but Jordan facing this problem very high for two reasons. One of the reasons, the topographical situation in Jordan, yeah, and the other one we can say in the presentation. The second issue in the Dr. Iyad said in MENA region, the field water sector has the share for, at the moment, 10% from the total energy consumption, and he expected in 2040 it will be more than double. So that mean the topic energy efficiency in pump and water it is a challenge for us, and we have to do something. And the pump manufacturer is starting with that, and we will start now with Mr. Trolli for. He said, I will go a step further. We will go from pump efficiency to generate energy, yeah, from the pump operation. Mr. Abu Shanab, he will say, I will have the efficiency not only in the pump but in the system, because the pump efficiency alone will be not solve the problem. So we will start with this topic, and then if we are finished, we will go to the water topic. Every presenter has 20 minutes. Please, not not extended. And end of the presentation, we will have discussion, 10 minutes or whatever. Okay? So, you can start.
Thank you.
I have
to the presentation. Yeah. Wait. Can you hear me? Perfect. Just waiting for a visual support for everybody. Okay. Thank you. Good morning, everybody. As already reported by Mr. Mogbel, my name is Samuele Torelli. I am sales responsible in SAER. We are an Italian manufacturer of centrifugal pumps and electrical motors. But the topic of today is related to a technical way in order to save energy and to create energy with the pumps. We started to develop and to explore this type of application because we are very, very sensitive today in the market about the energy efficiency and also the power consumption of every plant. You know better than me how much the current it costs today everywhere, and how much it is important also to spare efficiency, to spare energy. So starting from a typical machine that is a pump, a motor pump, we can use the same technology in order to produce electricity, because everywhere in the water distribution system pipings, it's common to have also water that must be wasted, because maybe you must move the water in a higher level because you need for some specific application, but some of this water is not used for your system. We are talking about any kind of different system, so for example, cooling system or distribution. In other situations, for example, you already have high quantity of water in an high level, like for example lakes, like digs, or this kind of situation. So, starting from existing pipings or existing systems, we can put in the existing pipings a pumps as a power generator. How doesn't works? Maybe switch it off. Yeah, sure. Like this. Perfect. So we start to develop this while we have a wide range of pumps that can be used in different type of application, because the type of pump that must be used for save energy and for create energy, the pump must be chosen according to the difference of pressure you have in the piping and also by the flow rate. How it works, basically, this kind of system. It is a normal centrifugal pump that is installed in an existing piping as a bypass. So, according to the difference of pressure you have in the beginning at the end of the piping, and according to the flow rate, the existing flow rate, so basically according to the size of the piping you have, we can choose a correct pump in order to restore and resave all the possible energy. The motor installed work as a power generator. So the pump is moved by the flow of the water and create current through the electrical motor. Why this kind of system? It could be a successful application, because of course in the market already exists the turbine for the power generation, for example in the big plants. But usually the power generation turbine are very expensive and are designed for a big flow rate. And this type of application is not completely suitable for the most common systems and plants that everybody has. We have, for example, in the municipal systems, in the water distribution systems, sometimes the flow rate are low, like, I don't know, 50, 100 liters per second, not so big as required by a big turbine. So to use a pump as turbine is the best way in order to resave and to generate current from nothing, basically, because this water usually are wasted. No? So, looking back to the system, this system can be self-controlled by an electrical system like a PLC, and can be controlled according to the quantity of water available, because in a lot of different plants and systems, the quantity of available water is not the same during all the day, because maybe, for example, there is or an irrigation system or a water distribution system where the end users ask and require for a lot of quantity of water during specific hour along the day, but in other hour there is an excess of water. So why don't transform this water in electricity, considering that during the day you spend energy for driving the pumps, and maybe during other period in the night or other period during the day you can resave and restore this energy, transforming the flow of the water in current. So the type of application are really wide, because we find this kind of opportunity in minings, in water supply, in water recirculation for cooling and heating, for example. Try to think, for example, here in your area you have a lot of mountains, no? So it's common to pump the water up to the hills because you need to provide the village and the home of waters. But some of this water, once is there, is not used, for example, during the night. No? Or, for example, in cooling systems, this is happen frequently in general industry. No? For example, you need to cool down specific plants where, for example, you produce energy. Usually you have also cooling system in order to cool down the systems. Usually these waters, once that have cooled the system you must cool, it's wasted. Consider that the different pressure you need in order to work correctly with a pump as turbine start from 8 to 10 meters. So it's less than 1 bar. And to have a jump of 10 meters is very common in the water system and water pipings. So this is the best way in order to save money also. And today to save money in the public distribution, for example, of water, but also in the private company is very, very important, no? For everybody. We have a lot of case histories, for example, for this kind of application, because we have an engineering department that can design and study which kind of pump it could be used for the specific application. And we can design also the complete system. But one of the most interesting aspects of this system is that it's completely simple to install, because in an existing piping it's enough to create a bypass, a parallel bypass, and to install the pump there. The energy that is produced by the system can be used directly by the customer, or can be also put in the network, similar to, for example, a solar plant or a normal power generation. No? Every country have usually agreement for alternative power generation systems. So the main companies, the big companies, but also the public company can create agreement with governments in order to sell the current. So it's a kind of rewash of your system, no? Because your system consumes current most part of the time, but the same system can also produce. According our calculation, usually in 2-3 years it is possible to save the same quantity of money you need to pay for implement this system in your existing piping. So 2-3 years is nothing related to the time, to the lifetime of a centrifugal pumps, because with the normal maintenance, a centrifugal pump can work for 20 years. And if you think, according, for example, some example we have, no? In this case, if we look at this case history, we have a flow in this application that is around 15-35 liter per second. That is a very low flow rate, no? With 5 bar of pressure, or differential pressure. So it means that the difference between the starting point of the system and the end is 50 meters, no? With this kind of small system that produce only 10 kilowatt, because it's a small system, you can save 50, 60, you can produce 50, 60 megawatt per year. It is a lot of current, no? And today, the current is everywhere produced mainly with petrol, gas, and in some countries with nuclear plants. But the world is very, very sensitive today about the efficiency of the power generation. So why don't use the most common systems we have in the world, that are the systems related to the water distribution? Another example, for example, here is an application in a mine. Also in the minings, it's common to have difference of heat, important difference of heat, because the minings usually are located in different heights. So in this case, with just 22 liters per second, we can produce up to 200 megawatt every year. No? The range of flow rate and heat is very, very variable. So it means that with our actual range of pump as turbine, we can cover flow rate really high, up to 1,000 liters per second. That is a big flow rate, but starting from real small flow rate, few liters per second, and the difference of head is between 8-10 meters up to also 300-400 meters of difference of head. Which pump can be used, if a single stage or a multi-stage, or which type of execution of the pump, is just related to the available flow rate, so available piping size, and the difference of head. Another interesting and important thing is related to the material of construction, because we have in our range pump as turbine made in different materials, so not only in cast iron, but also in stainless steel and in super duplex also. Why it could be very, very important to have available the super duplex and the stainless steel? Because this kind of implementation, this kind of system, it could be used also with sea waters. and daily are more important in the world to use seawater for production of, for example, potable water. And and it's very common to use seawater or salty water also for industrial application, for industrial plants. I think, for example, in city like Aqaba, for sure there are a lot of industrial plants that use seawaters. But if you think this water at the end of the cycle, it is wasted usually. Not really wasted, but pumped again in the water, in the sea. Sorry. So why don't use the residual pressure of this water in order to produce electricity? So we as a company, we can provide not only the product, but also all the engineering of this system. So we can have the companies like public company, like municipal company and so on, but also the private company to design and to implement this system in the actual pipings. I don't want to be too concentrated in the range of the pumps because it's just in order to show you that the type of pumps it must be according to the existing system. So it is very, very important to design the system in order to spare more possible energy. Consider that usually the average efficiency of a centrifugal pump, and my colleague Philo will talk about this, no, is around 75 and 85%, more or less, depending by the type of pumps. A pump as turbine lose a little bit of efficiency compared the same product used as pump, but is around 5-6%. So it means that you can reuse the 70-75% of the real power you have hidden in the water. No? So it is very, very important, and a lot of systems in the world now are going to moving because, for example, we are from Italy, no? And in Italy we have a lot of production of electricity with the water jumps. But when a system is designed for this, they use big turbines, and the big turbines are some complicated and very, very expensive. Try to think that, for example, for a small turbine, it's simple to pay something like $150 to $200, no? $1,000, of course. But for smaller plants, it's not simple to find on the market a turbine designed for small flow rate. To use a pump is the most efficient way in order to recuperate the energy. I stop myself. If someone of you have some specific question, I'm available, of course. Yeah, sure, after you. Thank you for your attention.
Hello?
Hello. Yeah. So, good morning, ladies and gentlemen. It's an honor to have the opportunity to address such a distinguished audience. Thank you for attending our session. Thanks also to Aqua for organizing this event. It was a really nice opportunity to meet with you all within the past 2 days. There was lots of exchange, sharing experiences, success stories, because we all have the same pain and same challenge. Yeah. And thank you also for the exhibitors, technology providers, that they were bringing also new technology, helping us to move forward and avoid any setbacks. So for whom that we didn't have the chance to meet, I'm Muhammad Abu Shanab. I will not introduce myself because it's already done by Mr. Amir Muqbil. I will start with a short presentation about the company, and then I'll jump into our main topic, energy efficient water supply solutions. So Wilo is a German company and one of the world's leading premium manufacturers for pumps and pump systems, focusing more on the building services, water management, which is our topic today, the clean water utilities and wastewater utilities, OEM and industry. The company started in 1872, which is 151 years back. And today we are 8,200 employees, between us 2,500 service technicians and over 900 service partners. With our innovative solutions, smart products, and our individual services, we move water in an intelligent, efficient, and climate-friendly manner. Wilo is already a digital pioneer in the industry of pumps. So we have 16 main production sites, 70 subsidiaries in more than 90 countries. So yeah, we have 3 factories in Germany where the company started, then in China, in India, in France, and Italy. Since 2017, also Wilo focused more on the North America region by having 3 factories. So for the people that they work also with USAID code 937, we can cover the demand of the country of origin required from the funds of USAID. We are relevant from water supply to flood control, from hospitals and schools to infrastructure, water and wastewater work. So our products are systematically important and an indispensable part of our modern life. Now, having the right product with a good efficiency in terms of performance, hydraulic performance, and also electrical motor, the prime mover, overall efficiency is on optimum level. We are focusing more now to make our solution smarter, which means the pump itself can control itself, can protect itself from possible damages, anticipating possible failures, and even control other pumps with easy data interface with your, let's say, BMS or SCADA system or our own dashboard. Also, we focus a lot on the customer satisfaction and the customer. So thanks for our smart pumps, which allows this data interface that, imagine you have a city of sewage lifting station, wastewater treatment plant, and biological treatment, water transport lines that you can monitor all these pump stations from anywhere and from any device. Good to mention here that Wilo is one of the 50 sustainability and climate leaders worldwide because of our sustainability strategy that we follow internally and externally. I mean, this sustainability strategy is reviewed quarterly and annually. In internal side, for example, we are planning to have by 2025 all Wilo production sites around the world to be carbon neutral. In fact, 3 factories are already carbon neutral now and certified by TÜV Nord. Thanks for the pioneering in exploring alternative energy resources, which is now available already in Dortmund facility, a hydrogen compact H2 power plant. And we also focus on the material waste inside our manufacturing. So you are not only getting an efficient pump and a sustainable pump, you are also sure that this pump is made in a sustainable way without any impact on the environment. In external side, we are also focusing on improving the efficiency for the pumps and making it more smarter, which help our customers save more energy and reduce the carbon footprint and the impact on our environment. Just passing by, German Sustainability Award Wilo was the winner for the German Sustainability Award in 2021. Now, we came to the main topic here. It's good to mention and to highlight that Wilo covers the products and solutions for the complete water cycle, in the water management, from raw water intake, extracting the raw water from the nature, then treating this water to make it with a good quality and distribute it in a distribution channel with good quantities to the end user, to the consumers, irrigation. And then on the wastewater cycle, we have dewatering and flood control, Also, wastewater collection and transport over long distances, downhill and uphill to the treatment plant to be treated and cured, then discharged again or be reused. So today we are going to focus on the blue side of the pie that we have today, the water cycle. And later on, if you are interested, we can schedule a webinar or something to discuss it forward in future. Yeah. So at the beginning, because this is, we share all the same pain and same challenges, I would like to start with the most important nexus that we are highlighting all over the sessions here, the water, energy, and food nexus, which is central for a sustainable development. Yeah, the demand on these three resources is increasing drastically because of the rapid global population and urbanization, economical growth, changing diets of the cities. The water itself is a very limited resource. So the fresh water available in our planet do not exceed 5% of the total water available, and the remaining is a saline, which needs maybe 9 to 10 times the normal rate energy consumption to produce it. And this limited water resource has to serve exponentially more number of people and usages. Yeah? On the other side, fossil fuel production is still dominant and growing part of the global energy mix, yeah, which is a very highly intensive water process. It needs a lot of water. Now, in terms of food, take a farmer or something, he needs to produce the vegetables, and he's paying more bills for the electricity, and then also for the water. He's raising the prices for the vegetables and the products that he's selling, and this is what we are experiencing in our Levant region and everywhere. So food, and there is still water to produce food, but food and nutritional insecurity still remains a widespread. Now, energy and water are connected in a very complicated manner. You know all that all energy resources needs a high amount of water to be produced. We are talking about powering turbines, cooling and thermal processes. We have the service site. We have also feed pumps for your power plant. So you need a lot of water to produce the energy. And energy itself, it's required to make the water resource from the nature available for the consumers. I'll take the water from the nature and treat it, make it with a good quality, and distribute it in good quantity to the consumers. So every single liter of water passes through a water supply system represents a significant energy cost and have a significant impact on the environment, on the economy of the country, and on the infrastructure as well. So this is just a start. Okay, now as a WILO, we have mega trends which we fixed for the upcoming 20 years. Water shortages that we have on our planet, energy shortage which demanding new efficient solutions, urbanization, people tend to move to big cities, yeah, which have all the services, but this is placing a substantial stress on the existing infrastructure. And also we have the climate change, which impacting the water patterns and the temperature patterns, rainfall, rainwater harvesting. So all of these challenges, actually there is only one key to solve it, or which can help us to solve, is the digitalization, which helps us to better or manage our energy and water demand. So, energy consumption, water supply system, it's a very important topic, and one of the big topics. The major cost in a water company is the energy consumption in the water supply systems. Now, water supply, it absorbs 2 to 3% of the global energy consumption worldwide, and this energy can be saved from 25 to 30% through an improvement of the performance of the existing stations completely, not only the pump. So, major topics in water supply, we already heard a lot of sessions about it. I just wanted to skip this slide, but yeah, water leakage, there is also some technology. that we can help us to, let's say, damp or a little bit reduce the impact of the water leakages in curing the pipes, etc. Optimization can be done to existing plants. If you have the best efficient pump in your system and you are operating it in a wrong way and you have wrong operation, you will still pay a lot of money in the service, also in the energy consumption. So sometimes it's worth it to look also apart from the pump into the system, what is your needs, maybe some optimization on the control side can help you save energy, yeah, just by changing the way that you control the pumps. And for sure, pumps is also the major part in the pump stations, which consumes energy. 80% or more of the energy consumption in the pump station is coming from the pumps. The lighting and other things is not really consuming that much of energy. So talking about the water supply, there is 4 main applications. Raw water intake, taking this water from the nature, whether it's from a lake, a river, or a dam. Then treating this water, yeah, and then distribute it to the consumers, and also the irrigation. And the raw water intake, we provide a complete range of pumps, depends on the application, and also a wide range of material of construction depend on the application or the type of water that you have. You should know the quality of the water, sand content, free passage or ball passage size of the pumps. So it depends on the application. For example, if you are going with the medium or jack well application, you can go for vertical turbine, deep well application, borehole pumps with submersible pump and motor, or vertical hollow shaft turbine pumps, which can go deeper up to 100 meter and more. In the water treatment, we also provide vertical mixers, horizontal mixers, feed pumps, transfer pumps, and pressure boosting pumps, which is also important for the performance improvement and reduction in energy consumption in your treatment plant. Now, water distribution and boosting is also a very important topic, and it depends on each country topography. As we said before, you select the best pump for your application and your operating duty point. And this segment is actually one of the biggest, let's say, absorption for the power and electricity compared to other applications, making this water available for the consumers. So, how to improve it? Okay, we have first from the design stage to a proper matching or proper sizing of the pumps to match your demand or future demand as well. Second thing, you can use the variable speed drives to control your pumps and work on a constant pressure with variable flow. There is also some intelligent monitoring system and control systems. Now, most of the pump stations that we are using today is just controlling the pump to have a constant pressure, for example, over a varying flow demand. But we all know if I have a pump station of 5,000 meters cubic per hour at 10 bar, the 10 bar is required when I pump 5,000 meters cubic per hour. But if I pump less flow, for sure I need less pressure. So sometimes it doesn't worth it, or usually there is a way to save more energy by pumping, let's say, with less pressure, not maintaining the pressure, because at less flow you need less pressure to deliver. So this is a way to do it, and of course you need also a very high efficiency in hydraulic side and also on the electrical motor side to reduce the energy consumption. I'll just have a review here about the total life cycle cost of a pump system. Now, as my colleague here told, the typical life cycle, typical lifetime of a pump is actually about 20 years, 10 to 20 years. And usually when the water companies think to buy the pumps, they will just send the tender, and then there is a price or initial capital price, capital investment, which let them make the decision to buy this pump or the other pump. But in the pumps, you should always look for the life cycle cost of 10 years or 20 years. I buy the pump now, okay, then it's only 8% of the total life cycle cost. 7% or more depends on the manufacturer or the system that you have, but the bigger contribution is going to energy consumption. So when I evaluate a pump compared to another pump, I should know exactly what I'm going to pay now and 10 years forward. Yeah, if you buy, for example, or this is also applicable for replacement. Yeah, if I have a pump station that is absorbing X power, so I need to invest, for example, 100,000. Yeah, 100,000 can be back to me within 2 and 3 years. If I don't do the action now and change the pump, 3 years later, I'm going to pay more. Yeah, because you are paying more for the electricity bills that you have. Taking a live example on this, we have a pump station in Germany which was replaced with a more higher efficiency pumps. The existing pump was also from Wilo, but it's an old one, operating duty point 220 meter cubic per hour at 90 meter head. Now this pump was with a 90 kilowatt motor having an efficiency of 78% hydraulic efficiency, which is usually a good efficiency compared to semi-axial impeller for the borehole pumps. So you end up with overall efficiency for the pump and motor 69.4%. Now at the same site, it was replaced with the best in class efficiency borehole pumps, Z2K pumps. At this efficiency with the CT coating, which is also improving the efficiency more, we got 87.1 hydraulic efficiency and reach an overall efficiency of 81%. Taking these two examples of each other with the curves of the pump, you can see the overall efficiency, 81 for the new improved pumps compared to 69. And with the previous electricity tariff in Germany, 0.17 euro for kilowatt hour, you are having back your investments in 3 years. And this is with the low energy cost. Now it will be less as much as the electricity will be more and more expensive. So this is an example that I had to share with you regarding the efficiency of the pump and the system completely, exactly. Another point is also reviewing your system data and inputs and the demands. This is an example for a treatment plant done by Veolia in Soviet country, and because of the reduction in the industry and the water demand, they were running an old suction pumps with a 630 kilowatt, but they don't need this much of flow rate and head. When you replace it with a vertical split case sized as per the current demand, there was a reduction of 355 kilowatts, which was restored after 8 months. So we have to really review our system as a complete system. In terms of the pump, it is actually 80% of energy consumption, but if I have the best pump with the best hydraulic and overall efficiency, but I don't know how to operate it, maintain it in a good way, and to control it actually in the best way, we will be also losing energy. So I think I'm almost done with my presentation. If there is any question, we can skip it later, but I have only 1 minute video that I would like to present, and I am done. Yeah, thank you.
go to the water treatment energy efficiency, we have two colleagues, Dr. Sulaiman. He said if we are using solar and thermal in desalination, we will have a good alternative for electricity. And Dr. Zuraikat, he said he will demonstrate how we can improving the energy saving and let's say optimization the energy consumption in wastewater treatment plant, and he has three examples for that. So we start with Mr. Suleiman. Thank you. Sorry.
This is not the presentation. It's not this one. The first one. Yeah. Thank you. Can you hear me? Yes. So first of all, thank you for having me in this very interesting event. It's my first time to participate in the Aqua event. And of course, thanks to all the audience, because without you, we didn't have a presentation. So thanks for having the time to join us. As our nice moderator, Mr. Amir, he was saying that we will start from system components and system management level. And now I will be taking you in a tour on the generation level of systems. So my presentation, as you see, it's called Integrated Supply of Energy and Water in Jordan, because I wanted to present today an example that we have done previously in one of our previous projects in Australia. And there is no better country than Jordan to replicate similar case, so I wanted to present the case study for Jordan. So about us, where we are located in the city of Aalborg, which is in Denmark, in the north part of Denmark, and our company name is Aalborg CSP, which is the same name of the city, and CSP refers to concentrated solar power. So we are actually working with concentrated solar power, not photovoltaic. So our main product is steam and heat and not electricity. Normally I stand with my presentation, so back to this slide again. So we are since 1988. I used to be longer, but yesterday I ate Mansef. So we since 1988 we have been working in the business of boilers, and we are actually a small company, but we are also with a large footprint. We have installed capacity of more than 200,000 megawatt thermal worldwide. Our headquarters is in Aalborg, which is the city in Denmark. We have an office in Spain, and we have multiple project management offices in different places in the world. So just a quick tour on our company history. As I said, from '88 we have been working in the traditional boiler design. This is actually where when we decided to move from traditional boilers to renewable boilers, which is basically known as the solar tower receivers on the top of the tower. So in 2007 we had our first steam generation system, which is based on a solar tower receiver for a large scale power plant, which was with a capacity of 6 times 50 megawatt electricity. We moved forward in 2011 with the district heating business. So we have built more than 4 district heating plants in Denmark. It's used for district heating to provide heating for the houses, also based on green solution. And in this case, one of the examples was based on parabolic trough. In 2014, this is, I would say, one of the flagship projects. It was a turning point and milestone for us
where we have built a system, complete system in Australia based on a solar tower system. So that actually the case I will be discussing in more details in the coming slides. But also one of our flagship references is in 2019, the largest CSP plant in the world, which is executed in Dubai, known as DEWA project in the Maktoum Solar Park. We were actually subcontracted to supply 600 megawatt electricity and 1800 megawatt thermal of steam generation systems, from molten salt to thermal oil and from thermal oil to steam. So basically a heat exchangers. And that's something we also work and fabricate. So in this slide, I hope to give you an overview of what services we provide and for what applications. So we are an engineering company. We provide solutions for different applications. Any application that needs steam or heat, like dairy manufacturing or mining industry, food industry or food processing, we have solutions for these kind of industries. One of the latest thing we have been working in my R&D department is we are working on a pilot scale system for a mining company in California with a capacity of 8 megawatt to provide steam that they will use in the mining process, because they want to have a transition from conventional mining to green mining. So they need a green resource of steam, and that's what we are developing for them in our R&D department. So that's what I say, probably the best in the system integration and sector coupling, so just in case. We can be your reliable partners from A to Z. From R&D, which is in my department, we perform feasibility studies and consultancy services. We have done that in different countries, in Saudi Arabia, in Egypt, actually also in Jordan, but also we have executed systems in different countries. And the reference list is too long, and I don't want to, maybe it's boring for you, so you can get it from the website. I will just show here the interesting part. But we also provide pre-engineering services, engineering and design, procurement and manufacturing. Sometimes we are also an EPC if the location of the plant makes sense for us, if it's in Europe. Sometimes if it's outside Europe, we provide EP services, and then the C and the construction can be done by local construction company. So for the Jordan case study, I've just made a quick research about the situation with the water, especially because we are in the Arab Water Week. So I have seen that you can see from the highlight that it's one of the world's most water scarce nations with around 100 cubic meter of water available per person. And also oil is the country's main energy source with 52% of total consumption. You can also see the references. However, I mean, it's also the same for the rest of the MENA region with the challenges, as my nice colleague also from Wheeler was saying. We are all sharing the same pain and the same challenge. But actually, we think, actually, in Jordan, your risk is your opportunity, because you have so much good natural resources, and you have a great potential as a country, as a location, to use natural resources. So how can your risk be your opportunity? This is what we are going to discuss. So what you see here in the slide, you have a very nice natural source, which is the sun. And this is a map of the direct normal irradiation, the DNI, which is actually the CSP technology is more caring about the DNI and not the GHI, like in the PV case. So the direct normal irradiation source, you can see from the slide, it can reach up to almost below 3,000 kilowatt hour per cubic meter, per square meter per year. So from 1 square meter, you can get 3,000 kilowatt hour per year. So how, if your risk is your opportunity, this slide can maybe explain how. So this is a little video I will play, and then we can discuss more details. So what you see actually in the video is a complete system that has been built in Australia. We got the project awarded in 2014, and we have finished it in 2016, so it's in a good operation since 2016. The basic application here actually for the client, he has a 20 hectare of greenhouse of tomatoes, and he's in the middle of desert in Port Augusta in Australia, and he needs to produce tomato, but he needs three main things. He needs electricity, he needs desalinated water from the Gulf of Port Augusta. He also needs heating for the greenhouse during the winter time. So actually we provided one system that gives him the three outputs. We provided a system that is based on the technology of solar tower receiver. And those who are not familiar with the technology, basically it's a solar field with lots of mirrors. Just mirrors, of course, this control system, but it's just mirrors. And the mirrors are responsible to reflect sun radiation to the focal point, which is the black and white receiver on the top of the tower you see here. And we feed water using a feed water pump. I hope it was here, it was Vilo. And then we use, the focal point is get it heated by the reflected sun rays from the mirrors, and we produce steam directly. So it's a direct steam generation system. And with the steam, then we go to the next slide. And then you can see the receiver on the top of 127 meters tower. So with the steam, we go to a steam turbine and we produce electricity. But then we don't waste the residual steam. We utilize the wasted steam from the turbine, and we drive an MED unit, which is a multiple effect distillation unit. In this case, the client needed 1,000 cubic meter per day of fresh water. So we are driving an MED using the hot water. It was a 6-stage. And then we we desalinate the Gulf water. But then the waste heat from the process of desalination, we recovered the waste heat and we made a heating network for the greenhouse or the tomatoes. So three in one. This farm actually produces 15% of the production of tomato in Australia, only from this system. So the capacity of the system in peak is 36 megawatt peak with 20,000 megawatt hour per year and 250,000 cubic meter per year of desalinated water, and that was the client demand. So how we can replicate this successful solution in Jordan? Yes. It's in Port, the farm itself is 20 hectares. Yes. But the area of the system, you can see the solar field has 51,000 square meters. Yes. But you can see the farm is, does that have a pointer? Yes. So this is the solar field, but this is the 20 hectares of the tomatoes farm. No, it's a Gulf water desalination. So actually this system is 5 kilometers away from the Gulf of Port Augusta in Australia. So, no worries, no. I like the discussion, but yes. From the Gulf, yes. No, it's from the Gulf. Actually, it's only 5 kilometers from the Gulf. Actually, it is 5 kilometers because the provider of the mirrors had a guarantee that the mirrors needs to be away from the Gulf 5 kilometers. Otherwise, it will be out of the guarantee. So that's the only reason why it was 5 kilometers away from the Gulf. So now we have the DNI map with the location of this system in Australia together beside the Jordan map of DNI. And then you can see that maybe it will be a very interesting location that we replicate such a system in Aqaba. So from the DNI level here, it's actually quite similar to Australia. So you can see you can still get a little bit below 3,000 kilowatt hour per square meter in the location of Aqaba. And this is a nice screenshot from Google Earth of potential systems because if you need water desalination, you need to be close to a water source. The water source could be a gulf, can be a sea, or can be actually underground water. But sometimes underground water is already usable for irrigation. Maybe you don't need to desalinate. It depends on the location. But we see Aqaba is actually a very potential location, especially it has also many industrial activities. And with the industrial activities also, maybe they need steam and they need hot water, they need electricity. And that something can be provided from such a system. So back to the title of my presentation, why it says integrated supply of energy and water. The nice thing about the CSP, it's like a Lego system. The Lego system is like you can plug and play. So actually, if you build the CSP system, you can still do an integrated or an integration technologies to the same system. So here in this slide, we can use the sun to provide the sun radiation to the CSP, and then from the CSP you can produce steam. From the steam you can produce electricity, you can desalinate water, but also you can hybridize the CSP with PV. Then you can actually optimize the system. By optimizing the system, I'm talking about optimizing the cost, because the cost of PV is much lower than the CSP. That's something for sure everyone knows. But the key is that the CSP comes with cheaper storage compared to the storage of electricity from PV. Actually, the levelized cost of electricity coming from the PV is maybe $0.02 per kilowatt hour, while the CSP can be 5 to 6 cents. But then this 5 to 6 cents is actually including a storage, and the PV doesn't include the storage. So that's actually the benefit. But we see as a company working in CSP that actually it is very sometimes optimized in cost and efficiency if you make a hybrid system with CSP and PV. Of course, depends on the application as well. But actually, these are only like 5 SDGs you can achieve from such system. Of course, you can achieve more. It depends on the application. But if we even want to make or explore more opportunities and more revenue streams, now we are talking about business case and income, then actually you can benefit from the hybrid system of PV and CSP. And now we have seen Jordan is also making some decisions and plannings for installing wind capacity. So actually you can even move forward to be a producer of a green hydrogen, which is now the whole globe is demanding a green hydrogen. And basically to get a green hydrogen, you need green inputs. You need green electricity, you need green water, and you can only get this from wind or CSP and solar. Of course. Yes. Yes. Of course.
Concentrated, and you can produce actually, like hydrogen from it.
Yes.
You can just basically take any metal oxide, treat it with water, and you actually get hydrogen. And this hydrogen will be cheaper. So the levelized cost of energy, which you are talking about, actually, it can be much better. So if you go to EDARMA as well, you're going to find that they are actually doing projects where they have 1.5 for the PV and for the storage is 3.5. The project is called 5 cent for production. So I'm not I don't agree with all what you said, but however,
it's good the discussion. Of course, I would like to elaborate more because, as you said, the CSP can come in different technologies, and of course, there is nothing comes without a price. Everything comes with the consequences. But then here we are talking about the alternative. If the alternative is diesel or if the alternative is gas, then this must be the best solution. We are not competing against the electricity coming from the grid or electricity coming from PV. We are talking about other opportunities. For example, if one day the CO2 emissions have value, which is in some countries does, and you pay a lot of taxes of CO2 emissions, this will be your only support or the only help you can get to avoid these high taxes. It's one last slide, and then actually this is this slide may be not very interesting for all audiences, but it is the way we see how the action plan can be. This is the way actually we work daily when we are executing projects. We have an action plan, and the action plan always starts, of course, with a study. We have, because the CSP is not a standard product. It's not like a pump you buy, or it depends. It's a tailored solution. It's not a function. If you're buying a function like a car or a pump, then you have a fixed price and it's just from off shelf. But for the CSP generation system, big systems, you need to make a tailor, so you need to make a study. And then, of course, with our access to a large consortium of EPCs and finance agencies, we can also provide the opportunity to get the finance from one of our networks. So that's it. I hope you enjoyed the tour, and I'm very much happy with the interaction. I'm looking forward for more questions and more discussions. Thank you.
First of all, thank you very much for a very interesting and informative presentation and technology, which I think this is very useful to Jordan. By the way, we started a small project with the Jordan Phosphate Company in Aqaba with CSP, combined with desalination. I hope to work and will be successful. But this is not my point. My point is to you, would the increase in the temperature of the water help in optimizing the cost effectiveness of the system? For example, if the seawater is in average 12 or 15, would a water source of 70 degrees make the system and the cost per kilowatt hour or cubic meter more cost effective?
So, for example, the location in Australia, the input temperature to the MED for the water who's driving the MED for providing performing the desalination, the temperature was 75 degrees.
This is not from the sea.
No, this is not from the sea. This is from the system.
No, no.
The sea temperature of the water,
before the
yes,
system.
the sea
That's
temperature of the water was between 18 to 20 degrees. So the inlet temperature of seawater going in is 18 to 20, but the water driving the MED was 75 degrees.
Okay, but just suppose the seawater is 70 degrees.
Yes.
Would this help the system? Groundwater.
You mean the 70? The water you want to treat? Yeah. Yes, of course, it will help the system. The higher the temperature, the higher the efficiency it gets.
Because in Jordan,
because the delta T's will be lower. Yes.
In Jordan, we don't have access to sea.
Okay.
But we do something more important than sea desalination, which is the deep groundwater aquifers.
Okay.
This is like 1,200 meters, 1,300 meters. I drilled so many wells with this gentleman.
Yes.
And these waters are of high temperature.
Okay.
Sometimes it's 65, 70.
Mm-hmm.
We use them in other areas, like the phosphate company,
Okay.
for mining process.
Yes.
But our interest is not agriculture, definitely, because
Yes.
we do have the best natural greenhouse in
Yes.
the world, in the Jordan Valley. But just to imagine with you this system converted just for drinking water supply with this high temperature of groundwater,
Yes.
would this make it more feasible?
Yes, the short answer is definitely. But actually now we are talking about a natural resource of water that comes with 75 degrees. The opportunity to use this water for different applications is so good. I mean, you can use it for a preheating. It's perfect for preheating systems that you can use for other applications that still needs hot water or needs steam, for example. So, yes.
So thank you very much.
Thank you.
Yes. Hello.
Can I have the pointer?
Yes, still good morning from my side. My name is Liad Al-Zregat. I am from the Technical University of Berlin. I will move now to the sanitation sector from the pumps and from the desalination options that could also work for Jordan to talk about energy saving and energy generation in wastewater treatment plants in the MENA region, but I'm taking Jordan as a case study. So we are looking at potentials and challenges. So wastewater treatment and reuse has a high energy demand. And if the regulation actually in Jordan gets stricter and requires further removal of contaminants, this will require also energy. So the aim is to improve the energy use at the wastewater treatment plants. But what are the reasons? So the reasons for energy optimization is that we are running empty actually of fossil resources, the energy crisis due to the war happening between Russia and Ukraine, the climate change raising the CO2 emission, and the financial burden that the wastewater treatment plant operators actually have. So what are the approaches? So in this presentation, I will talk about energy audit and energy analysis as an approach. Secondly, I will go to utilizing the energy embedded in wastewater. And then I will talk about hydropower as an option, as a green option, but also not excluding solar and wind energy. So, wastewater treatment plant is a municipal energy consumer number one. So what are the steps to improve the energy use in wastewater plants? Step one, reduce energy consumption and estimating saving potentials. We can do that and unlock that only by conducting energy audit and energy analysis. This is the first step to do. And second step, to look at options to increase energy efficiency, or increase energy production, and that by looking at different options like hydropower and biogas. And there we are talking about anaerobic pretreatment and digestion or co-digestion option. But we should not forget that wastewater treatment plants actually are done to purify wastewater. So we don't want to work on the energy aspect and forget about the water quality. So I will take you now through 3 research projects that 2 of them have been conducted, were conducted in Jordan, and 1 ongoing project. So the first project was conducted in 2016. It was about energy audit and energy analysis for optimizing energy in wastewater treatment plants in Jordan. It was funded by the Ministry of Environment from Germany. So the scope of the project was to conduct energy check for most of the wastewater treatment plants in Jordan. And the second step is to have energy audit and energy analysis of the wastewater treatment plants. In this project, we selected 2 wastewater plants as case studies. And by conducting this step, we can demonstrate optimization potentials and recommend different optimization measures. And these measures could be measures for increasing energy efficiency and measures for energy generation. So the first step was to do an energy check for the wastewater treatment plants. And these are based on the German Association, the worksheet from the German Association for Water, Wastewater, and Waste. So we followed their procedure for conducting energy check. And they have also, we also followed their procedure for the energy analysis and energy audit. And we at the Technical University of Berlin, we took this worksheet and we developed an Excel sheet that actually is processing the data from the energy audit and energy analysis, and to work with them and get easily the output from this process. So the first output is the energy check. So if we look here, okay. So if we look here, we have the red line here is around 20 wastewater treatment plants included in the energy check, and we have the guide value of 34 kilowatt hour per population equivalent per year. If we take out the trickling filters, do not include them in the wastewater treatment plants, the line moves, the blue line moves to the right. So we have even higher specific energy consumption per capita per year. And that's actually all our activated sludge wastewater treatment plants. They require high energy, and this is why it shows that performance is like the median that should be for Jordan is 40 kilowatt hour per population equivalent per year. And we selected actually 2 case studies. Actually, any wastewater that actually falls above this guide value should be subjected to audit and energy analysis, and look for energy optimization measures. And as I said, Mu'tamazar wastewater treatment plant was selected, and Aqaba wastewater treatment plant, as well as 2 case studies for the energy analysis and energy audit. And this is some pictures from the energy audit that we have conducted. We can see from the first glance that, as example, the sand trap here is over-aerated. We can have an immediate measures just to turn down the airflow into the sand filter without going into so many details. And so this is from the walkthrough in the wastewater plants. And, sorry? Which one? Which one here? Okay, good. So we're collecting the information. So see, there's like some common work for energy optimization. And this is like we start collecting data from like submersible mixer, from blowers, from pumps, and so on. So after doing that, we collected the energy, the audit output, the data from energy audit, and we put it on our Excel tool. And we found out that the energy distribution in Aqaba wastewater plant in 2015 is about 70% of the energy actually goes to the aeration. So used in the aeration tank. And 20% is basically it's under others, but in the Excel tool, it's the irrigation pumps. Because Aqaba use the water and pump to different users, different end users, so it takes a lot of energy, and this is the second actually highest energy consumer in Aqaba wastewater treatment plants. So if we look at the energy analysis and look at the as is status in 2015, and look at the minimum ideal value and maximum ideal value, we come out with 25% energy saving potential for Aqaba wastewater plants. So there is potential, and we have to dig in and look what are these potentials. So we have recommendations for energy efficiency measures, and we classified them for 3 categories. The first category is the immediate measure, as I showed in the slide before. We can just reduce on the spot directly the airflow, so this could fall under immediate measures. And it does not really cost that much, nothing actually. And short-term measures by changing a pump from an old efficient pump to a higher efficient wheelie pump, as example. Yeah, that's it. And as a big investment, we can have, as example, change the aeration system from surface aerators to pressure aeration. So this is selected recommendation based on audits. In Aqaba, because we didn't have that much funds, so we went to the short-term measures, which is actually installing a regulator and oxygen sensors to measure the oxygen concentration in the aeration tank. Because they didn't have, they measure it by hand, and it was an instant measures, and then maybe after some hours again. But this will give you a continuous reading for the oxygen concentration. And by doing that and connecting this to SCADA system, the operator can turn off, turn on, reduce the speed of the aerator, and so on. So we reduce the energy consumption by this. So these are the selected recommendations based on audits. Is either optimization of the existing blower surface aerators, control and regulation, replacement of blowers, surface aerators, like go from surface aeration to pressure aeration, and mixing as example, adjustment of rotational speed of agitators, replacement of agitators, and pumping. And maybe have an efficient pump, that's what Wilo, my colleague here, Mohammed, presented. We can also implement an efficient pump going from 60 or 69% to 80% efficiency. This could be also help in optimizing the whole energy efficiency of the plant. And of course, if we have a dewatering plant, we can select the optimal polymers and efficient technology for dewatering. So I'll move now from energy efficiency, energy saving, to energy generation. So we're trying to use every single option that a wastewater treatment plant has. So a hydropower, this could be an option. So we conducted a field study. It's called like the hydropower potential analysis of wastewater treatment plants in Jordan, and was funded by the GIZ. So the scope was to identify energy production potential of hydropower turbines in wastewater treatment plants in Jordan, take 5 case studies, and analyze, also in-depth analysis of these 5 case studies. And we made also a market review for the technologies available and their specification and their applicability. At the end, we did a feasibility study of energy generation from hydropower turbines. So this is just for the background. This is potential location at wastewater treatment plants, either at the upstream, as before the wastewater treatment plants, or at the downstream after the wastewater got treated and transported into reuse line. We can place that turbine at the end of the reuse line. As example, there is also a potential to place turbine maybe in between the treatment units if the conditions are there, head and the flow. So this is shortly, because it's like I don't have that much time, just the highest potential, the outcome of this project. We see that Kufranja wastewater plant has a downstream around 1 million kilowatt hour per year could be generated, and this is at the downstream, and there is also at the upstream. This could be also energy could be generated. So I'll move. This is Kufranja. So this is the outlet. This is the first junction box so far away from the treatment plant. So we are talking about 400 meter above the sea level, and here is almost 122 meter above sea level. And afterwards, the DN90 goes to DN400 and continues downstream beyond the Kufranja dam, where the level there is almost minus 30, I think, minus 30 below the sea level. So to move to the second options for energy generation in wastewater treatment plants, we are talking about anaerobic, integrating anaerobic pretreatment to increase energy efficiency and performance of wastewater treatment plants. Yeah. I'm about to finish, actually. It's the first, just some slides, 3, 4 slides. But yeah, this option could be for the MENA region, but we can apply it in Jordan and this ongoing project. So the aim is to develop a novel climate-friendly approach as of anaerobic with a post-treatment. And the objectives of this work is to reduce energy demand by incorporating an upstream anaerobic treatment. So demonstrating potentials, reducing operational costs for the operators, improving sludge management. This is also an issue in this Arab Water Week was also mentioned, and improving the overall treatment plant performance. This is the partners, and these are the benefits. I will mention just some of them. This is a fundamental lower energy demand. It produces very low excess sludge production, and it reduces greenhouse gases, and could be incorporated in or integrated in existing treatment plants that are actually 33 wastewater treatment plants in Jordan. And this could also improve the effluent quality of the wastewater. To sum up, meeting the new effluent limits and strict water quality standards increase the operational cost of wastewater treatment plants. Benchmarking, it should be the first step before going into any step with optimization, because based on that, then we move forward to energy audit and identify optimization measures to increase the energy efficiency of the treatment plant. So, increasing the share of renewable energy also could reduce the total cost of the wastewater treatment plant itself by using renewable energy. And again, integrating anaerobic unit upstream for the existing wastewater treatment plants will reduce the energy consumption and improves the effluent of the wastewater treatment plant. And thank you for your patience. Bye-bye.
My question is for Mr. Turelli, because probably his talk is the most interesting, because I was in Nashua, New Hampshire, and you bring fond memories of trying to harvest all the energy from hot water drainage and pumped hydro, Niagara Falls from Nikola Tesla till now, and all the revolution of Edison Energy, General Electric. I've been there in Boston, and everything you talked about probably is applicable. Now in Jordan here, we pump water in, for example, Daht Rashid, there is a huge, reservoir. Actually, I live next to it. So I was always, I go to the ceiling and to our top floor and say, why can't I just pump all that energy out of there? If you have running water, you have energy. And more even so, if you have running hot water, you have energy, because you can actually, harvest this energy. So this is an excellent point. For you, sir, actually, we are 3 people that worked in Virginia Tech on technologies related to hydrogen. One of them, Samir Sarhan, he started the company with Linde Group, and he became the president of a company after that, and then he is now running Qudra in Saudi Arabia Air Products, and he's funding like $4 billion in Texas, building some, reforming for hydrogen plants. And he's actually, number one, and I call him the king of hydrogen, in the world, no question. His friend is Ayman Ma'aita, probably, he signed with Masdar, where he actually called, concentrate power. He called it Ayman's concentrate power. I told him to call it after my name, Amjad concentrate power. So if you say CSP, maybe it's ASP. Remember our names, Ayman and Amjad. I was in this group, by the way, and I used to run programs for them. So the problems with CSP, it's very well documented, and people actually shifted to the photovoltaic, and there is no going back to the CSP unless it's fixed. Now, Elon Musk is building, lithium ion in Australia. So you talked a lot about Australia, and they are actually moving from lithium to sodium. So the energy storage is going to go down. The cost is going to go down. I assure you it's going to go down because of the number of projects that EDARBA is doing. So the 5 cents project is going to achieve its goals. And driven by Elon Musk and Tesla, actually, their test bed is in Australia with their virtual power plants, with their mega packs and their power packs, their cars, bi-directional charging, etc., distributed generation. So many technologies. I think it's going to be much better than the solution that they have in Al Maktoum, where they use molten salt for storage. Although they say that's better, but I don't think it's going to, survive for long. Thank you, sir.
Yes, it was. But you already said whatever is must said. Wherever you have some water that are not used, and also if you think, for example, the big lakes that are used also for storage, for agricultural and so on, usually you must to keep the level. And if you look at, there's always wasted water. Wasted is not wasted, but everywhere you have a transfer from different level is an opportunity to produce electricity. And we started this development because some partner of us in the world they asked to us to engineer the pumps in order to use it as turbine, because today, or if you are building a power plant, and of course there are manufacturers of real turbines, but the turbines are really expensive and are designed for big flow rates for these kind of applications. So sometimes also really few small application with a few liters per second can be used also for a simple farm, for example, no? Because exactly.
Turbines for the wind, and if you need any backup power from diesel with Rankine cycle. So it's actually a published paper, and it's a very excellent paper.
Yeah.
It's based on the load, and it's actually we used some neural networks and artificial intelligence to come up on the best solution, and actually it beat the grid requirements, which was I think we calculated to be 20 cents.
Yeah, sure.
It was less actually.
And also the application of the system could be simple, because it's enough to have some directional valves that can control the minimum flow rate, so that the system can start when you have enough flow rate and can stop automatically when you have no water enough. So, and the cost of a centrifugal pump is really low compared to the rest of the system, because the rest of the system you already have usually, no? And this is why. But one of the best application, for example, is the heating system, the heating and cooling systems. Also, for example, in their application, you always have water that is used in order to transfer thermal power, no? And this water have an end. So why not to reuse?